Hi, and welcome to Tellurium Tutorials.
In this video, I'm going to show you how to model a cycle in which moiety is conserved
Of a cyclic system where moiety is conserved. In chemistry, a moiety is described as a subgroup of a larger molecule. In this figure, the moiety is a protein. This large circle can be considered the moiety. During interconversion between the phosphorylated and the unphosphorylated protein, the amount of moiety remains constant. More abstractly, we can draw a cycle in the following way. This is another moiety conservation cycle, where S2, S2, and S1 are cycle species. The two species, S1 and S2, are conserved because the total S1 plus S2 remains constant over time. This occurs at relatively short timescales because over longer timescales, protein synthesis and degradation would occur. However, at short timescales, which we are analyzing in this, the moiety is conserved. An example of such a cycle where moiety is conserved is the adenosine triphosphate, adenosine diphosphate, and an adenosine monophosphate cycle. In the AMP, ADP, and ATP cycle, the adenosine backbone is conserved, while the phosphate groups are added and taken away throughout the cycle. When analyzing the rates of change of S1 and S2, the following two simple differential equations arise. Let's zoom out so we can see this better. So, when you try and solve these two, it appears that the rate of appearance of S1 must be equal to the rate of disappearance of S2. Therefore, when the computer tries to calculate this, it will not be able to do so. This means that whenever S1 changes, S2 must change in opposite direction by exactly the same amount. During a simulation, the sum of S1 and S2 will therefore remain unchanged. Computationally, we need only explicit one of the differential equations because the other one can be computed from the conservation relation. Whichever differential equation is chosen, however, the species left out must be computed algebraically by using the conservation law.
Now in Tellurium, we're going to define our model. We're going to say S1 goes to S2, and S2 goes to S1, two different steps of the cycle. Now I'm going to do the rate. Now I'm going to create the rate laws, which are defined by those differential equations from before. Okay, this is the forward direction, and this is the reverse direction. Now I have to define the constants. Okay, so for the initial conditions, S1 equals 3, and S2 equals 0. Then K1 equals 1, K2 equals 0.606, N is 1, VM1, VM2. Okay. Now we just need to go r dot simulate. That time is not important. Okay, now when I run this, we can see that we have the two things approaching the new steady state. Thank you for watching, and now you know how to model moiety conservation cycles using tellurium.